it's coming up. So Yifang, we can see your slides day of the symposium. And this day, the second day, the morning of the second day will be dedicated to future colliders. So we're going to have 2 talks about future colliders. And then we are going to have talks about different efforts of doing this strategy planning in different areas of the world. So we are very happy to have Professor Yifang Wang from the High Energy Physics, the Institute of High Energy Physics of the Chinese Academy of Sciences, Beijing, China. And he's going to tell us about this effort, this planning to build a circular electron-positron collider in China. So please, Yifang, thanks for accepting the invitation, and go ahead.
Thanks very much for the invitation. I'm happy to give you a status update of the circular electron-positron collider in China. So the idea actually came out in 2012, almost 12 years ago, and we have been quickly gained the momentum afterwards in China and also in the world. So the idea is looking for the a collider, firstly based on electron-positron collision, and afterwards, if we have any kind of indication of new physics, we could move to the proton collider with the energy all the way up to more than 100 TeV. So since 2012, we have been moved ahead with a kickoff meeting in the year of 2013 and pre-CDR in 2015, a CDR in 2018, and now we are in 2023. We have released our technical design report. So the plan is to have about 10 years of operation at the Higgs energy. And then we move to the Z for about 2 years. And then afterwards, we are going to take 1 year of data of the W and another 5 years of TT bar with a major upgrade. So by having this kind of operation plan, we can have something like a few millions of Higgs and a few trillions of Z, and afterwards we have hundreds of millions of W and about 1 million of TT bar. The physics with this kind of data are the following. So first of all, we can study the Higgs coupling with great precision. The improvement can be an order of magnitude better than the current high luminosity HC. And we can also do a direct, indirect probe to new physics up to tens of TeV, which is also about order of magnitude higher than that of high luminosity HC. And we can make a precision measurement of electroweak parameters by a big improvement on the precision. So we have prepared physics white books for the Higgs, and others are still in the preparation for the flavor physics, QCD, and the electroweak, etc. So these kind of machines can have a very good study of the new physics. For example, if we do with the SMEFT fit, we can get a clear improvement over existing measurement. You can see from this right bottom picture. And Higgs is actually a very good probe to new physics. For example, for dark matter searches, for electroweak phase transition, and for exotic decays of Higgs, and also for many other searches. So indeed, you can see that very rich physics coming out from these machines, and it's not just a precision measurement, as many people thought that the Higgs physics is just the precision physics, but it's not only. We have a lot of new physics searches we could perform at this machine. The design of the CPC is the following. We have about 100 kilometer circumference of this circular collider, which has a much higher luminosity than the linear collider. And indeed, the 100-kilometer circumference is optimal circumference. And you can see from this picture, right bottom, indeed, the effective cost for each Higgs is in the end the minimum at about 80 to 100 kilometers. That's why we choose 100 kilometers with a good opportunity also for the future of the PP collider. And in this same tunnel, we can have both machines share the same tunnel, and we can have the operation of the Higgs, WZ, and top with a switchable kind of operation. So our baseline is about 100 kilometers circumference, 30 megawatt, upgradable to 50 megawatt, and high Lumi Z, and also a TT bar. So the design of the SRF system is in such a way that we can switch between among the different operation modes, say from Higgs, W and Z, TT bar, you can switch back and forth. And with this kind of, let's say, bypass scheme, you can show from the left bottom, we have the freedom to, let's say, start from, for example, a Z measurement for the calibration, and then afterwards works on the Higgs precision measurement and come back for the Z for another calibration, etc. So this kind of arrangement actually give us a lot of flexibilities for the physics programs in the future. For such a machine, of course, SRF cavities is a major technology advancement. So we have been working on the new technology called the mid-temperature baking technology, which is actually easier for comparing to the nitrogen doping, and with very good performance. You can see from these two pictures at the right. For both 1.3 gigahertz and the 650 megahertz, we have been managed to produce prototypes with specifications exceeding the requirement for CPC. We also produced SRF modules with cavities in it, both 650 megahertz and the 1.3 gigahertz SRF modules have been produced, and you can see from the left bottom the achieved performance is actually more than what we have specified for the CPC booster, and indeed it is even it is also better than LCS2, Shine, and other projects. So basically, the performance is almost one of the best in the world. We have been also working on the high efficiency klystrons, which could save us a lot of funding for the operation. The first prototype with the efficiency of 62% has been successful. And later on, we have been working on the second prototype with the higher efficiency. Very recently, we managed to test this second prototype of the klystron with CW mode and power, the power of 800 kilowatt, and also with the efficiency of 78%. So you can see from the right bottom, the efficiency has been in a very good agreement with the simulation. So this 78% of the efficiency for the new klystron is going to be a major technology advancement for our machine, and we believe that this technology can be used also for other machines in the world. In addition, we have been working on many other R&Ds. You can see from this picture, we have prototypes for the collider dipole magnets, the booster dipole magnets, and also other equipment like the EM deflectors, Lambertson magnets, quad magnets, and the vacuum pipes. Indeed, many of the technologies has been tested at our Beijing Electron Positron Collider and also at the high energy photon source in Beijing. So you can see from this picture, the high energy photon source has been completed the construction, and very recently we have seen the beam current storage at the level of 13 milliamps. So this is actually a major test of our technologies like magnet alignments, vacuum pipes, net coating, electron gun, and so on, and the BPMs and etc. So this is actually a very good test of technologies for the CPC. We also had made a lot of effort trying to build a green accelerator. So experience at the high energy photon source is the following. We installed solar panels on the roof of the building. You can see from this picture at the right top. And the total power is 10 megawatt, which gave us about 10% saving of the electricity bill. We also installed a permanent magnet with a total saving of 5.6 gigawatt hour per year. And we also use the hot water for heating. And indeed, the total hot water is more than what we need at HEPS. But unfortunately, the habitants nearby the light source is not that dense, so we are not able to use this for the city use. So we are actually looking for other possibilities. And indeed, we have the R&D for the CPC, including high efficiency klystrons, as just said. We're also working on the energy recovering klystron, the solid state transformer, and the permanent magnet, so on. And then we try to design and the R&D of a cooling compressor plus heating pump system to recover hot water in winter and cooling water in summer for the use at light source. We are continue to investigate power generators using very low temperature hot water. For the detector, in addition of the three common used concept like IID type of detector and the SID type of detector, and also the idea concept, we came up with a new concept. We haven't come up with a good name for it. We call it the fourth concept. The idea is the following. We would like to improve the detector performance, in particular for the calorimeter. For the EM calorimeter, we are going to use crystals instead of other, say, detector technologies. So the energy resolution can be improved from, let's say, 10 to 20% over square root of E to less than 3% over square root of E because of the crystals. And these crystals have been arranged in a way that it can be used using the PFA kind of technologies. For the hadron calorimeter, we try to improve the energy resolution from 50% over square root of E to 40% by using new technologies. I'm going to talk about this later on. So having all these technologies, we try to have a very good energy resolution of the calorimeter and also novel detector designs based on PFA calorimeter for BMR of 3 to 4%. Of course, we have a silicon detector and so on. So for the vertex detector and tracker, these are all silicon technology based. We have been working on different technologies. For example, the chips called the JetPix 3 and 4. They've been Tai-2 PICs and so on. So all these technologies show that we managed to achieve about 5 micron energy, the position resolution, and they have been tested at the DESY and other places. For the calorimeter, as I said, we are going to use rectangular arranged crystals. So the incident particles came in to this kind of crystal arrays. And by having this crystal, we can have a good energy resolution. But also by reading crystals at both ends and with timing measurement, you can have a 3D shower information with limited readout channels. And the shower separation can be reached less than 4 centimeters. For the hadron calorimeter, we try to use scintillation glass. And by doing this, we can increase the sampling ratios at reasonably low cost. So the energy resolution can be improved to a level of 40% over square D. We had R&Ds of this kind of crystals, and they can see from left bottom, the figures, we reached about the density of 6 gram per cubic centimeter and the light yield of about 1000 PE per MeV. So this kind of performance is already somehow close to the crystals, except the light yield. But for hadron calorimeter, we believe that this kind of light yield is acceptable, and R&D is still going on. The schedule is following. We try to finish all the preparations for the proposal by the year of 2025. And hopefully in the year of 2026, the project can be approved and we can start the civil construction after that. And during the 15th 5 years plan of Chinese the economy, we should finish most of the civil construction at the beginning of the 16th 5 years plan. And then the detector construction and also accelerator will be continued all the way up to the end of the 16th 5 years plan. So hopefully by the time of 2035, we can start the experiment. We have a reasonably good team. Currently, about 400 people from China are working on the project. And we believe that we have another 400 people coming to join us in the next few years from other projects. Hopefully, we are going to have thousands of international collaborators once the CPC is approved. And IHEP is actually is a host lab with experience managing international collaborations such as BEST-3, Diabe, and Juno, and also accelerator projects such as BPC2, spallation neutron source, and the light source. We propose a temporary management structure as shown in the right bottom figure, where we have the project director controlling the accelerator detector and the theory, and above the director, we have steering committee and also institution and board. In the future, we may have also funding committee above us. So this is a scheme proposed and endorsed by the International Advisory Committee. We are actually eager to have a large international participation to this project. And we already have some kind of contributions from the international community to the CDR and TDR. We have many MOUs signed with international organizations, the groups, and we have collaborations on physics, detector, and also for the accelerator. International committees, conferences, workshops. We are also members of many international collaborations like CALIS, ILDTPC, and RNRD collaborations, and in addition to the LHC experiments. We have been actively involved in the European strategy update and the SNOMAS process, and also many other workshops. We have been working with a lot of industrial partners and the suppliers, both domestically and also internationally. So we have been talking to them. And many of the results we have been obtained up to now with R&D has been a result of the collaboration with many of these industrial partners. The details of the CPC accelerator has been shown in this technical design report that's been online. Everybody can have access to it. The total cost is about 36.4 billion RMB, which is roughly about 5 billion euros or dollars, in which you can see from the right top the table. The project management contains something like 3 billion RMB and another 200 billion RMB for the accelerator, 100 billion RMB, sorry, it's not 100 billion, it's 10 billion and 19 billion, 0.3 billion, and then another 0.3 billion for the gamma ray beam lines, and 4 billion for the experiment, and 2.7 billion for the contingency. So all the details can be found in this document. So in summary, CPC addressed most of pressing and critical science problems in particle physics. Accelerator design and the technology R&D are reaching maturity. TDR completed, and we are almost ready for construction within the next 3 years. The reference detect TDR is in the preparation to be completed by next year for the proposal of the 15th five-year plan. Strong and experienced team backed by IHEP and the international teams schedule will follow China's 15th five-year plan, and we will continue to work with the government for funding and funding agencies to get support. Thank you.
Actually, Fang, and this was an impressive talk. So we have time for questions from the audience and from the Zoom audience. Any questions? Yes, Edgar.
It wasn't clear to me. You mentioned hot water being needed. What was that for?
Oh, we generate the hot water from a cooling system of the accelerator, and we hope that this hot water can be used by general public. So some of this hot water has been used by our lab, but we hope we can supply this hot water for general, let's say, normal habitants. But because the light source facility is actually away from the city, so it's hard to find the user at this moment. But hopefully in the future we can find them.
The light source was impressive. I was impressed by the first time I saw the photograph of the light source. It was really amazing. Even the yin and yang symbol in the garden was amazing. So I have a question about this site. Are you looking for, do you have sites already that they're exploring? Or
we have been explored almost 5 to 6 different sites, and we haven't had a final decision. In our TDR, we have 3 sites seriously investigated with also a cost estimate. But the final decision has to be a result of the negotiations with the central and the local governments, and it's going to be a process in the 15th five-year plan.
Okay. And just one more question, out of curiosity, how much does it cost the 1 Higgs boson? Because I couldn't figure out from the plot.
It's not cheap, so, but I don't remember exactly. Let me see. This is 100 million.
What units?
100 million. Total cost, 100 million.
Oh, what unit?
RMB.
Okay.
So this is the total cost. It's not per Higgs, but anyway, this is the power and so on.
Okay, so it's not per Higgs.
It's not per Higgs, but you can divide. It's only 4 million to 5 million Higgs. So each Higgs is actually, I would say, many thousands of dollars, let's say.
Okay. Excellent. So any further questions for Yifang? From the Zoom audience, anyone? Just raise your hand, virtual hand. Okay, so I don't see any questions. So let's thanks again, Yifang, for this very nice talk.
Thank you.
Okay,
Bye-bye.
thank you. Yifang. Okay, so the next talk is by Professor Christophe Grojean. Just arrived in his office at DESY today or yesterday from CERN. And he's an expert at FCC and has been involved in the planning of FCC for a long time. So Christophe was kind enough to agree to give us a talk about the future circular colliders. Thank you, Christophe, and the floor is yours.
Hello.
Oh,
Can you hear me? Yes.
yeah, we
Okay.
can hear you and we can see your slide. It's not full screen, but we can see it.
Yeah, but probably it's easier this way.
Okay.
Okay. So good morning, good afternoon, or good evening, everybody. It's nice to be virtually in Sao Paulo to discuss about the future of the field. And I would like today to present briefly the Future Circular Collider option at CERN. So of course, I mean, physics-wise, there is a lot of similarities with the Chinese project that Yifang just presented, but I will say a few words. I will focus more maybe on the physics than on the technological aspect. So what is a Future Circular Collider? For those of you who are not totally aware of it, it's a versatile particle collider housed in a 91-kilometer underground ring around CERN. On average, it will be something like 200 meters underground. And it will be implemented in several stages. First, it will collide electron and positron to become Higgs electric flavor top and QCD factories that will run between 90 and 365 GeV. And that's what we call FCCEE. And then, the electron and positron will be replaced by proton to reach a very high energy, maybe 100 TeV, maybe 120 TeV, depending a little bit on the magnet that will be available at that time. And that's the FCC-HH phase of the project, right? So a little bit of history. So the project, I mean, started actually in 2011, so before the Higgs discovery. If you remember what happened during the summer in the winter, there were some rumors about the Higgs boson 140 GeV, and few people at CERN, in Geneva, concluded that it will be perfect to build an E plus E minus Higgs factory, to really study this new object. And then few years later, in the European Strategy Update in 2013, actually people had the project, to build a 100 TeV PP collider. And then they say, well, now we will have the tunnel, and maybe we can actually house E plus E minus Higgs factory in the same tunnel. Then a few years later, a conceptual design report for the FCC physics case was produced and submitted to the 2018-2019 European Strategy Update. The European Strategy Update basically concluded that having such a Higgs factory will be of very highest priority, for the field. And then maybe this E plus E minus Higgs factory could then be followed up with a proton-proton collider at the highest achievable energy. So the CERN Council actually agreed on this strategy and is trying to implement it. And he recommended a technical and feasibility study that started 2 years ago. And then last fall, we had this midterm report, 700 pages document that was produced and submitted to the council. And very positive feedback was received from the council, right? So indeed, I mean, 80 to 100 kilometers is what you need to accelerate proton up to very high energy to 100 TeV. But it turns out that actually it's also the right size for E plus E minus collider for various reasons. First of all, it will allow you to get enough luminosity, 5 times larger than what can be achieved in a 27-kilometer tunnel, to maybe get sensitivity to the Higgs self-coupling. So the first time that you will reach 5 sigma sensitivity on the standard model value of the Higgs self-coupling, but also to get sensitivity to the electron Yukawa coupling and to learn about sterile neutrinos also. And furthermore, you will be able to produce in this tunnel something like 10 to the 12, 10 to the 13 Z boson. So it will be a tera Z factory that can be used then as a most powerful and most abundant flavor factory on Earth, right? And also having such a large tunnel allows you to have transverse polarization to be available all the way to the WW threshold. And this is an essential element, for instance, to get a precise W mass measurement that will feed all the electric precision test. Right? And then with such a tunnel, you will also be able to reach the 365 top pair threshold. And maybe you can even go a little bit higher in energy, right? Something that you cannot accommodate certainly in the LHE tunnel at the moment. You will be limited by the RF and etc. But that's something that you can achieve if you are at your disposal 100 kilometers, right? So after the success of the LHE, we certainly need a broad, versatile, and ambitious program that will at the same time sharpen our knowledge of already discovered physics. So that will be the guaranteed deliverable aspect of the project. But at the same time, we will also push the frontier of the unknown at high and also at low scales, right? So it will be exploration of the unknown. And together, FCCEE and FCCHH combine these two aspects. So it will provide more precision, more energy to reach more sensitivity to new physics. And the precision aspect sometimes is underscored, right? Underappreciated, but there is several examples in the history of physics where actually major discoveries were done via precision. For instance, in the past, new planet in the solar system were discovered via the precision measurement of Uranus, right? Some fundamental laws of new physics were also discovered. For instance, general relativity emerged from the study of Mercury perihelion precision measurement. And for particle physics, clearly you can say also that the Higgs boson was almost discovered or was clearly predicted by the precision measurement of the W and Z interaction to the quark and the lepton, right? So clearly there is a good case, to achieve precision measurement with the already known particle of the standard model. And maybe there is no loose theorem like at the time of the LHE or SSC, but there is certainly the promise to make important or significant progress in our understanding of fundamental laws of nature if we study with very good care of all the standard model particles. Right? So let me briefly comment about the feasibility study, right? So as I already said, it really emerged from the last European strategy update, that concluded that Europe and the world should go for an electron-positron X factory. And indeed, I mean, the CERN management launched this feasibility study with a midterm that took place 2 years ago. So what was the objective of this feasibility study? First of all, to demonstrate that you could build this collider both from the geological, technical, and environmental and administrative point of view, right? And then there is the question of the optimization and the design of the collider and injector chains. You want to study whether you need a new injector or whether you can rely, for instance, on the LHE as an injector for FCC. And you want clearly also to establish a consolidated cost estimate of the of this project and to draw the funding and organization models for such machines. And then, of course, the last step was to establish the physics and the detector concept for both colliders, right? For FCCEE and FCCHH. So a good fraction of time, went on into designing the collider, or where to put the collider. And, as I already said, it will be located around CERN, and there is various constraints. I mean, there is a Jura on this side, there is a lake that become very deep as soon as you go away from Geneva. There is the Alps in this area here. There is also some regional protected area, where you cannot have even a collider, even underground, because there is nice animals or nice plants living there. So there were various constraints that, limit really where you can locate this collider. And this, amounting to a machine learning optimization process, to study and to implement and optimize various parameters. And at the end of the day, it was concluded that the best place would end up into a 91 kilometer ring, with 8 surface points and 4 interaction points where, you will have some detector located, right? So then there is some discussion that has been going on with the various communes, along this collider circumference, to make sure that people agree to host this collider without too much damage, with the people living nearby, right? And at the moment, there is various geological studies, that are going on with some drilling in the various places, even under the lake, to really have a clear map of the underground status of the rock, to make sure that you won't end up into water, for instance, when you will be drilling and drilling this collider, right? So these are going on at the moment. There is various studies that are taking place. Another important aspect is actually all the environmental consideration, because at the end of the day, there will be a lot of excavated material, and you want to understand, for instance, what you are going to do with this excavated material. And there have been some studies, for instance, that are concluded that if you mix this excavated material with some fungi, then maybe you can reuse this excavated material to produce some fertile soil that you can use, for instance, for agriculture, or that you can use to build some new forest, for instance. Then there is also other aspect of environmental consideration that you need to take care of. For instance, what about the heat? So Yifang already mentioned, the heat water, the hot water that will be produced. Here, there is also some studies that are going on, with local population, clearly to heat the local houses, the local schools, the local hospital, but also, the local factories, in particular the cheese factories that need some heat to grow some nice comté or some nice cheese around in Jura and Haute-Savoie, and clearly they have some good expression of interest along these lines, right? So about the optimization, so you also want to make sure, that you don't need to build too many roads to have access to the collider, to have access to all the experimental points. And here again, the optimization was done and concluded that you need to build less than 4 kilometer new departmental road to run this collider safely. You also don't want to have a power outage when you will run the colliders. You want to make sure that the light won't be switched off in Geneva, for instance. And there have been some nice study going on with this French electrical company, RTE, just to make sure that it won't disturb the electrical grid nearby. But also, you don't need to build nuclear power to fuel these colliders, right? So nice studies has been going on around this line, and they have been documented in these feasibility studies. About the civil engineering, there will be some tunnel boring machines that will work in parallel 24 hours a day, 7 days a week, and they will progress at a rate of 18 meters a day in the molas. And so this means that you need about eight years to actually build this 91 kilometers tunnel, right? At the end of the day, there will be 13 shafts, to access the tunnel, and there will be 2 large and 2 small caverns where the collider will be located. So it will be really a 4 interaction point project, right? And here you can see a very complicated and very tight schedule, between 2032 and 2040 to deliver the tunnel in such a way that really the collider can be installed safely and then operated a few years later. So this feasibility study, concluded in this 700 pages document that are organized along 7 chapters. There is a placement scenario, the civil engineering, the implementation with all stages, the technical infrastructure, the collider design for FCCEE, discussion about the FCCHH accelerator. The cost and financial feasibility is in a separate document because this is highly confidential. And finally, there is a chapter about physics experiment, about 100 pages, and then there is 70 pages of references, right? So nobody wants to read the 700 pages document. So the FCC team has been asked to produce an executive summary of 44 pages that has been reviewed and read by various committees. The Scientific Advisory Committee and the Cost Review Panel met in last October. Then the Scientific Policy Committee and Financial Committee of CERN met in November. And finally, the CERN Council got a very executive summary. You know, every time a committee meets, they produce a summary of that contain half of the pages of the document that they receive. So the CERN Council received a couple of pages that has been read by several members, right? What about the physics experiment and detectors? So it was built around the three main deliverables that were asked by the CERN Council: the documentation of the specificities of FCCEE and FCCHH physics case, the strategic plan for the improved theoretical calculation, because it's not enough to build the machine, but you also need to have all the theoretical tools that are needed to exploit this machine, to exploit the data that will be collected in this machine. And then a large effort now is currently put on to defining actually what the detector should be to achieve really the measurement that are needed. Okay. And as I say, I mean, this report has been read by various committees, and they all concluded that it's a very attractive project. And even the financial committee, underlines the need to make the project attractive from the physics point of view, independently of the price it will pay, right? It will cost. So various important people, came to CERN. For instance, the French president and the Swiss president met with Fabiola Gianotti and concluded that it was important really for Europe to take some leadership and also to develop some international project worldwide, attracting, as CERN always did, attracting really some international cooperation, right? Even the US agreed and signed a very important document in April saying that they want to join the project if it is meant to be feasible after the next European strategy update, right? So what is the way forward, right? So it's a busy time. We are in 2024. The European strategy update is about to start, and we will have this expression of interest from the various detector collaboration, where we expect actually the first conceptual design report from the various detector in 2041, the technical design report in 2035, then the installation in 2041. As I said, the ring will be totally dug in 2040, so it will be ready for the installation of the various detector, and we will have the first commission in 2045. So we are only 20 years away from the first collision, right? This is the organization chart. This feasibility study is organized along several pillars. There is physics, experiment and detector, accelerator, technical infrastructure, all state processes and civil engineering, and organization and financing model. So for physicists like me, it was really interesting to see how such a project emerged, and where you need really the cooperation of various people, various kind of people to make this project a reality in a sense, right? It's not only in the head of physicists, that think of detectors or think about luminosity of the experiment, but you really need to get various people from various competencies together, to talk to the general public, to talk to the politician, to really convince that this is a project that is feasible and that is, of course, interesting scientifically, right? So as I say, it's really a CERN project, but with a very strong and international enterprise from the beginning. And at the moment, there is more than 140 institutes involved in the project, even a few already in America, in particular in Brazil, and also in Latin America, in Mexico at the moment, right? But clearly, this is the right time to get engaged into the project, because you can really have a huge impact on the project itself. I mean, at the moment, we are really designing the detectors, etc. But it's really the time to propose a nice measurement that can be performed, nice detectors, nice detector technologies, etc. that will be implemented in the final project, right? So discussing about a little bit about the physics, right? So exactly like Yifang was mentioning for CPC, which really a characteristic of a circular collider is that you have a very high luminosity at low energy, in such a way that, for instance, within a couple of years, you will be able to collect 10 to the 13, 10 to the 12, or 10 to the 13 Z boson at 90 GeV. This means that you will be accumulated all lab data. So you will redo all the lab program in every second minute when the collider will be running, right? But what is really interesting is that after the Z run, you will have exciting and diverse physics program with different priorities every few years. You don't need to spend 15 years at the Z pole or 15 years at the X pole. You can really switch back and forth, and within 1 or 2 years at each energy run, you can really achieve this program and accumulate enough statistics. So how much statistic it is, right? So I already mentioned this 10 to the 12, 10 to the 13 Z, but you will also produce 10 to the 8 WW pairs. You will produce more than 1 million of Higgs boson at 240 GeV. You will produce something like 100,000 of Higgs boson in vector boson fusion at the 365 GeV run. And of course, you will also produce about 2 million of TT bar pairs that allows you to study with great accuracy this top quark, with allows you to measure all this top quark coupling to the W and the Z that will be used later on, at FCC-HH, for instance, to measure the X-self coupling, because you need to know the top Yukawa coupling, and to know the top Yukawa coupling, you need to know the electroweak coupling of the top quark, right? So clearly, it's an impressive statistics. You can achieve all this physics program within basically 15 years. But for that, you need certainly to develop a lot of things. Monte Carlo generators, software and computer simulation, detector requirement, detector concept, controls analysis, lattice simulation, a lot of theoretical calculation. With the current knowledge of electric processes, you cannot really exploit all the statistics that will be collected at FCC-EE. And of course, there is also a lot of progress that need to be achieved in the machine detector interface, right? So all these things are happening at the moment. There is some fantastic progress, and we can really be ready in 15 years when we will be able to build this detector and start collecting the data. So the physics program can be summarized along three main area. The X factory aspect, clearly, I mean, it is sold as a X factory, but as I already said, you can reach the 365 GeV energy to study the top quark. And what is really fantastic at a circular collider is all the high statistics that you can achieve at low energy, in particular at 90 GeV, that makes FCC-EE really an intensity frontier machines, right? And of course, there is interconnection between these three areas, right? So the intensity frontier aspect is sometimes underappreciated. So first of all, you will repeat all the electric and QCD measurement, even though it's an E plus E minus factory, actually you can achieve QCD factories that you cannot do at LHC. For instance, non-perturbative fragmentation of the quark and gluon fragmentation function, it can be measured with high accuracy at these FCC-EE machines. And of course, you can measure with great accuracy the mass of the Z, the width of the Z, the number of effective numbers of neutrinos, all these asymmetries, the mass of the Ws, etc. So all this program that started at LEP and that now will improve by more than 3 orders of magnitude at FCC-EE. But having so many Z boson, you can also study very light and very quick couple new physics which will be coupled to the Z boson, right? So for instance, axion-like particle, dark photon, heavy neutral lepton, long lifetime particle, you will have a direct access to all this new and very appealing new physics sector, that is not the prime aspect of LHC, that was built to discover new physics at the TV scale. And so far, we haven't seen any new physics in this area. So that's why there is interesting new physics that can be actually hidden at much lower scale. And you will have access to this interesting new physics that could address the hierarchy problem, that could address the dark matter problem. You will have access to this new physics sector, thanks to this intensity frontier aspect of FCC-EE. But you could also repeat all this flavor factory measurement, because you will be producing so many bees and charm meson from the decays of the Z. I mean, that you will actually have, the most the largest intensity compared to the Bell 2 or LHEB that will be built in the future, right? And you can achieve B physics measurement or tau physics measurement with unprecedented precision, right? But to achieve all this physics program, you need to build the detectors, right? The appropriate detectors. For instance, if you're interested in this light and weakly coupled new physics, you need to have a detector with good hermeticity, good tracking, a good calorimetry. If you want to do flavor factories, you need good vertexing, good tagging and energy resolution, good hadron identification, right? So all these aspects now are being quantified and really, come up with specific detector requirement for all this aspect of all this physics program. So this main baseline run, the Z run, the WW run, the ZH run, and the TT bar run have been documented in the CDR already. And in the meantime, there are some new ideas to actually exploit this collider at different energy. For instance, having a dedicated run at 125 GeV, to produce the X as the S-channel resonance. And this will give you a unique access to the electron Yukawa, reaching the standard model sensitivity within 1 or 2 years of a dedicated run. You could also look at the ZH, close to threshold, 217 GeV, to have access to the X line shape. Basically, really look at this threshold and see and measure with great accuracy the X mass. But you could also run the collider at lower energy, below 90 GeV, to have access, for instance, to achieve some non-perturbative QCD precision measurement, right? Precision studies. Right? So that's the collider aspect. But there is also the idea now to exploit this machine in a non-collider way, for instance, using the electron from the injector for beam dump experiment, or to extract the electron beam from the booster, or to reuse the synchrotron radiation photons. So some ideas along this line, have been now been done to compare, for instance, to other facilities like Petra 4, which is a very hard X-ray machine, and you can see that FCCEE can overcome this machine by several orders of magnitude, in particular in the very energetic regime, up to 100 of keV X-rays, right, photons, right. You could also study strong QED, so in the strong field limit, and compared to other facilities that have been proposed at the moment, like this LUXE project at DESY here, that want to study basically QED close to the Schwinger production pair. And you can see here that FCC can be really used to do that in a more intense way, with a repetition rate which is 3 orders of magnitude higher than this LUXE experiment, right? There is also the idea of using FCC as a new source of positron or even positronium that could be used to do some precision QED measurement, or to a machine that could be producing some positronium Bose-Einstein condensate. And when you alienate this condensate, you could have a 500 keV gamma ray, very powerful gamma ray laser, right? And there is also the idea of using this positron and positronium as a non-destructive nanoprobe in material science, right? So there is really a project which is much richer than simply a collider, right? A high-energy collider. Nonetheless, I mean, for what is it designed for at the moment is really in particle physics, and you can use and explore, light new physics like axion-like particle that will be produced in association with the gamma or with the X. And you can see that FCCEE will really complement the constraints that are coming mostly from astro and cosmology, which are the most constraining at low energy, for masses of the axion that are below 1 MeV or 1 GeV. But for masses above that, you need to rely on collider, and clearly FCCEE will be the most powerful collider to produce or to explore this unexplored region of parameter space. Also for sterile neutrinos, so this heavy neutral lepton, that might have something to do with the masses of the active neutrinos via the seesaw mechanism, for instance. And here you can see that FCCEE will be able to really cover the region of parameter space that is predicted by the seesaw mechanism, right? So you will be able to give a clear answer on the origin of the mass of the active neutrinos, for instance. But of course, I mean, FCC will be also X factory machine. So the X will be produced mostly at 240 GeV, something like 2 million of them. But you can also use the run at 365 GeV to have access basically at the production via vector boson fusion. And there is actually a nice complementarity between the two runs, you know, because it will help you to leave some flat degeneracy among the various couplings. You know, if you have a run at 240 GeV, you know, you cannot necessarily disentangle the various X coupling, but adding the few extra events at 365 GeV, you know, you can really separate the various operators that modify the X couplings, right? And here you can see really the improvement by a factor 10, basically compared to what will be achieved at the end of high luminosity LHE. But on top of high luminosity LHEs, you know, there are things that really an electron-positron machine can achieve that an hadron machine cannot achieve, like the absolute normalization of the couplings, you know, because you have a direct access to the width, you know, via this Z recoil measurements. So you have a model-independent coupling determination, right? And at the end of the day, as I say, really what is unique to FCCEE is access with the electron Yukawa via the dedicated run at 125 GeV, right? And then, I mean, that's not the end of the story. You can also do nice X physics at FCCHH, you know, because FCCHH will be the truly ultimate X factory producing more than 1 billion of X boson, and through that you will have access to, you know, very rare decays of the X boson, you know, and also very rich kinematical region of the X boson. You know, for instance, you will have more than 1 million of X boson that will be produced with a PT above 1 TeV, right? So that's really unique to have access and, you know, and do some analysis with a clean sample and a small systematic uncertainties, right? Okay, very quickly, this electric precision measurement, you know, clearly you can see here's the improvement compared to the current knowledge of electric precision, of electric measurements, right? You know, you will have, for instance, access to alpha QED at the Z pole with an accuracy of 10 to minus 4, 10 to minus 5, right? So more than 2 orders of magnitude better than what is currently known. And there, you know, you can indirectly use this electric precision measurement to search for new physics. For instance, pushing the mass switch up to 70 or 100 TeV indirectly via the measurement of the X and the coupling of the W and the Z, right? And for instance, you know, you could also be sensitive to new particles, you know, that don't necessarily couple to the Z, but they will generate operators, and those operators will mix, you know, via the renormalization, they will mix with operators that actually affect the physics of the Z boson. So indirectly, you can really have access, you know, up to masses of 90 GeV or 80 TeV to vector-like particles that don't necessarily couple to the Z boson via really this renormalization group evolution that affect all the electric precision observables, right? Then you can also see the prospect in flavors, you know, unprecedented statistics, you know, and also a nice kinematic enrich, because you will be producing all this B and charm meson with a high boost that will be used, you know, to tag all these objects, you know, even if you have large missing energy, for instance. And here are some numbers that really give you the improvement on the various measurements that will be performed, in particular in tau physics, right? Then, of course, at FCCHH, you will have a direct access to AV resonances, you know, reaching something like 40 TeV for some supersymmetric resonances, for instance, right? And you could also search for extra X's, you know, and there will be a factor 10 improvement compared to what will be achieved at high luminosity LHC, right? So overall, I mean, FCC is really the right project, you know, for the advance of the subject and the future of CERN, it really a good answer to the current situation that emerged after LHE, that has been producing the Higgs and nothing else. So clearly we need to be exploring physics at very high energy, but also exploring physics with very high accuracy to have access maybe to light and weakly coupled new physics. So maybe history will repeat itself. In 1991, we had this CERN Council decision that really concluded that LHE should be built. So maybe in 2028, we will have a similar decision of the CERN Council, really launching the start of FCC as a CERN project for the future of particle physics worldwide. So thanks a lot, and ready to answer some questions if you have some.
Thank you, Christophe, for this comprehensive talk and also for the midterm report. Amazing document. So we have short time for questions from the audience and online questions. So Ferdinando.
Yeah, I do have one. So at some point in the past, we had a plan for FCC hard-on electron mode. Is that still ongoing, or we have really focused on the EE and HH mode?
So this is not part of the feasibility studies. This is not part of the main run plan. Let's say we'll really focus on FCC-EE, and the idea is to go directly to FCC-HH. If, of course, the magnet technology is ready at that time, right? So if the magnet technology is not fully ready, then maybe there will be the time indeed for electron hadron machine in addition. But it's not part of the main project as it is now at the moment. Nonetheless, I mean, there is some R&D that are going on to establish also the physics case of this machine that is happening at CERN at the moment, yes.
Christophe, just curiosity, what's the accuracy on the measurement of the Yukawa coupling of the electron can be achieved?
We will reach 5 sigma the standard model sensitivity, right? But for that, I mean, you need a dedicated run, which is again not part of the run plan. If you look at what was written in the CDR and documented in the feasibility study, these are the main 4 energy run. And if you want to have access to the electron Yukawa, you need a dedicated run at 125 GeV. Which comes with some challenges because you need a very good control of the beam energy, for instance, smaller than the width of the Higgs, right? So for that you need, for instance, some dedicated monochromatization of the beam, but this is studied, and there is some nice progress that has been made. There is also some nice studies, for instance, you can use some polarization of the beam to enhance the sensitivity of the electron Yukawa. There is a recent paper along this line. So yeah, at the moment, as I say, it will require 1 or 2 years to reach a standard model sensitivity, but there is some room for improvement.
Okay, thank you. So any questions from people online? Or any further questions from people in the audience? I don't see any. So let's thank Christophe again for this excellent speech.
Thank you. Thank you.
So now we move to the part of the program where we will have reports of similar efforts on strategic planning from other regions in the world. And the first talk on this part of the program is going to be by Professor Hitoshi Murayama, who led this P5 planning report for high energy physics in the United States. So thank you very much, Hitoshi, for joining us. I understand it's late for you, and so thank you very much for joining us. And the floor is yours.
Okay, can you hear me?
Yes, we can hear you.
And
we see your slides.
Okay, wonderful. Yeah, so as thank you for the introduction, and as was already mentioned, I was the chair of this panel called the P5, which stands for Particle Physics Project Prioritization Panel that reports to the Department of Energy and National Science Foundation in the United States. So we finished this report at the end of the last year, and I would like to just give you a report on what it contains, what the process was like, and also how this has started to be implemented by the Department of Energy at this moment. So just to give you an idea on how the future planning process works in the United States, we always start with the community, and we conduct what we call the SNOMAS community study, which is organized by American Physical Society, Division of Particles and Fields. And it's called SNOMAS process only because we used to meet in SNOMAS, Colorado, but that is a mountain resort which became so expensive, and physicists can't afford to go there anymore. Well, so we actually meet in places like Minneapolis and Seattle these days, but we still call it SNOMAS process nonetheless. And after we community get together and talk about our aspirations and what we'd like to do, what is exciting in physics, what kind of projects that can be done, and so on and so forth, without giving any attention to actually the cost and how the program would fit with each other. And then comes a charge from Department of Energy High Energy Physics Division, as well as the National Science Foundation Division of Physics, with a specific budget scenarios, so that we have to come up with a program for particle physics that would fit within this budget scenario, together with the charge. And so that charge goes to a body called the Particle Physics Project, a body called the HECAP, and HECAP stands for High Energy Physics Advisory Panel. And that is a standing committee in the United States to advise DOE and NSF on issues related to particle physics. But there's actually a federal law in the United States that would demand that all the meetings by HECAP need to be done in the open. So it is actually not a suitable venue to discuss sensitive issues like prioritization among the projects, which has to actually be done in a closed sessions. So that's why the HECAP can create a sub-panel. So HECAP itself is a panel. So there's a sub-panel under HECAP, which is now called the Particle Physics Project Prioritization Panel. And that's what I actually chaired. The HECAP used to be chaired by Joanne Hewitt, and she appointed me in consultation with the funding agencies. And Joanne and I together actually selected the panel members on P5, and that's how everything got started. And at the end of this process, of course, we write the report that goes back to the Department of Energy and the National Science Foundation. But of course, we hope the report is written in such a way that is readable and accessible to wider audience, so that it gets read by people in Office of Management Budget, which is sort of the like Ministry of Finance in many other countries, Office of Science and Technology Policy, whose the director is actually a presidential science advisor. And of course, the budget gets decided by Congress in this system. So we hope that the congressional staffers would read it and also become sympathetic to a program, so that they would actually appropriate budget for high energy physics at the end of the day. The SNOMAS process started in 2020, but because of the COVID, it actually went on for 2 years. So even though it's called SNOMAS 2021, the last meeting was held in the summer 2022 instead. And you see a huge number of physicists getting together, and coming to this stage, there have been already 1,800 letters of intents and 548 white papers written, and more than 1,500 people have been involved in this process altogether, out of about 5,000 to 6,000 physicists working on high energy physics in the United States. And at this meeting that was held in Seattle at the University of Washington, there's an officer, Harriet Kahn, from Department of Energy, who gave a presentation on what are the key elements are for a successful P5 process. So she told us that process has to be well informed by the science community. That's why we went through this SNOMAS process to basically fish out what people want to do. We need to set a grand long-range vision for the United States particle physics. We need to face budget constraints realistically, so that we can say community made tough choices. And indeed, you can see in a few minutes what kind of tough choices we had to make. And we need to come up with a balanced portfolio. And balance can mean between domestic and international projects, and also among scales, small, mid-scale, and large projects. And finally, she said the community engagement is critical to success, because what she said was Pickering scientists get nothing. So the community has to be unified behind the plan that P5 would come up with. And you already see that it's actually a contradicting requirements. We have to say no to many things because we have to need to make tough choices, but still we need to make sure that everybody's happy with the plan, and that seems almost completely impossible to me. And so the budget scenarios also was quite difficult for us. So this is the kind of the budgets we can anticipate in the near future, given by these budget scenarios by the agencies, how much money we can spend on constructing new projects. And the red one is what we call scenario A, where A stands for awful. And blue one is what we call scenario B, which is better. And just by looking at, go ahead, somebody spoke?
No, we're just laughing.
Oh, okay. So just by looking at the projects we have already been doing all along, that already more than saturates the budget that are given to us. So for the next 5 years and so, we can't really start anything new. But from the year 2027 and beyond, there is definitely room to start something new. And so if you actually put everything together, what people propose at Snowmass, and we actually had to exclude the idea of building a Higgs factory on the US soil already early on, which would be like 4 times beyond this budget profile, we clearly couldn't afford. But even after excluding the Higgs factory, we still overshoot the budget by many factors, at least by factor 3 or so. So that's why it is clear we have to say no to many different projects proposals from the community. So already from the beginning of the process, I was aware that I was going to be the most hated man in the community. So working with Joanne, we came up with a panel, which was very diverse in terms of scientific expertise, geographic region in the United States. We already also had the 5 international members, 1 from Japan, 1 from Korea, 3 from Europe. And so this is the panel we worked together, 30 of us, and we made sure that we always reach a consensus at the end of the discussions. We had to have many, many tough discussions on its way, but we never voted on any issues. We always try to come up with a consensus, which we actually managed to do. And in the next talk, there will be a discussion by Paris on European strategy update. And there are some differences from the European process, the US process. So the US process actually cover a broader scope of science that includes particle astrophysics like dark matter CMB, galaxy surveys, and so on. And it actually follows the Snowmass study organized by American Physical Society, while the European strategy process is a monolithic process that are conducted actually by the charge from CERN's council. So that's also a different aspect of that. And we also need to face in the US process, this is meant to be quantitative exercise with the budget constraints. So it is a scientific prioritization, but at the same time, it's meant to be a budget exercise. So to understand the budget of various proposed projects as much as we can, so we actually constituted yet another subcommittee under P5 that actually studied cost and risk of some of the large projects proposed to us. So J. Marks, some of you may know him, he was actually one point the director of the LIGO laboratory, and he also was the project manager for STAR experiment for RIC. So he actually managed many large projects. We also got actually many members of this subcommittee that actually had led accelerator projects, the collider detector projects, particle astrophysics projects, nuclear physics projects. So there was a lot of expertise on this subcommittee looking at sort of how reasonable the cost estimates are. And the standard joke in the US is that when physicists submit some estimate of the cost, and that is always off by factor of pi. So we at least had to do it better within a factor of a year at least. So that's how we actually had to come up with this subcommittee, which turned out to be extremely useful. So even if we don't actually necessarily believe in either the proposed cost or assessed cost by the subcommittee, we at least get a very good idea on how mature the cost estimate was. So in that respect, it was extremely useful. And we chose the panel members from all different regions and different fields and so on and so forth. But we specifically asked them that they are not representing a particular country or field of collaboration, unlike the European strategy process. So they are meant to be just an individual science of excellent caliber and good judgment. And they are supposed to work for the good of the whole community instead of their own subfield or subregions. And we had to actually conduct 4 town halls in person and 2 additional town halls on Zoom. And then that was followed by 4 closed meetings by the panel members alone, so we could really talk through all the issues and prioritization process. And after 4 closed meetings, we basically converged on what the plan should be. And then we followed up by many additional Zoom meetings every week to finish writing the report. So one of the first things we had to do in the report is to define who we are, what are our interests, what we like to actually achieve in the field of particle physics in a US context. And of course, particle physics traditionally has been always about breaking things down into smaller and smaller pieces. And this is what we call the science theme of the search for the quantum realm, because we always need to go to the quantum regime of smaller and smaller microscopic objects. But in the US context, which is different from Europe, but on the other hand, it may be actually rather more common to the South American, Latin American process here, that we actually have the particle astrophysics component to it. So in this US context, we really would like to embrace this science trying to illuminate the hidden universe that has to do about dark energy, dark matter, the inflation, and so on and so forth. So that's another science theme we have in a US particle physics program. And you all know that on the left-hand side, we have the standard model of particle physics. And also on the right-hand side, we have the lambda CDM model of cosmology. But we already know that either of these theories are actually incomplete because there are many other issues we have to address. And at the end of the day, we need to come up with a complete picture that encompasses all the way from the microscopic physics to macroscopic physics. So these 2 wings have to intersect somewhere. And that's where we need to actually explore new paradigms in physics to get a complete picture. So, and we took 1 word from each of the science themes. And that's the way we came up with this title of exploring the quantum universe. And in each of these science themes, we have 2 science drivers. For deciphering this quantum realm, we need to reveal the secrets of the Higgs boson and elucidate the mysteries of neutrinos. In order to illuminate the hidden universe, we need to determine the nature of dark matter and understand what drives cosmic evolution. And to explore new paradigms in physics, we need to search for direct evidence for new particles and pursue quantum imprints for new phenomena. And so this set of graphics is something I actually had to work very personally with the graphic designer quite a bit. And if you actually look very closely at the graphic, you see the Higgs potential over here, where the Higgs boson from the Big Bang got stuck at the bottom of this potential. You see neutrons propagating, which is particle and wave at the same time. You see dark matter building a skeleton of the cosmic evolution over here, and you see gravitational wave permeating it. And the center of it can be viewed as a collider experiments or Big Bang, and you may see some big black holes coming out of it. So this was actually meant to convey the richness of physics, which is intentionally allowing for multiple interpretations, but it's too complicated. So for the purpose of the branding, we need to drastically simplify it to this simple logo with 3 triangles, 2 triangles. So these the magenta triangle is focusing on going to smaller and smaller things. The cyan triangle on the right focuses on things getting bigger and bigger, like the universe, and they intersect in the middle, and they are not inseparable. So we need to actually look at the complete picture with these 2 triangles together, and that's the sentiment being conveyed by this logo. And the first recommendation, our main recommendation, was to really make sure that we can complete and harvest science from the ongoing projects. But in terms of prioritization for the next exciting initiatives, we came up with a list of 5 in this rank ordered list. The highest one is CMBS4, which is really meant to look at the earliest moments of the universe, where the universe itself was of a quantum nature. And once you actually see the impact of gravitational wave coming from an inflation, that's the first evidence from quantum gravity. So that is an exciting science. And second one is what we call the re-envision second phase of DUNE for the long baseline neutron oscillation experiments. And I'll tell you what I mean by re-envisioning it. And then comes an offshore Higgs factory. I already mentioned that the US-based Higgs factory is something we decided we couldn't afford. So that's why we would like to be involved and working with international partners, such as FCCE, that Christophe mentioned in a previous talk. And unfortunately, in the current political environment in the United States, we couldn't mention the Chinese project, which I'm sure Yifang talked about, and I already explained to Yifang why we couldn't do that. But if we had mentioned it today, then that would probably result in some political backlash from the Congress. So we felt that by not mentioning the CEPC in the recommendation, we actually preserve the possibility to be involved in CPC in the future if the geopolitical situation would improve. So that was the intent behind this. And also that we need to actually make decisions rather quickly, looking at the timeline Christophe mentioned, without waiting for the next P5 report in 10 years from now. So I will come back and talk about another process that can that is designed to make a quick decision before we wait for 10 years in the later recommendation number 6. I come back to talk about that. And for dark matter experiment, we recommended ultimate generation 3 experiment, and we said because there were 2 proposals based on xenon and argon. But again, looking at the budget profile, we couldn't afford both of them at the same time. So that's why we recommended G3 experiment, and that would actually reach the neutrino fog. And finally, we also mentioned IceCube Gen 2, which is a neutrino astrophysics project, but also can be used as studying the nature of neutrinos at the same time, as well as for the indirect detection of dark matter. So that is the list of the major initiatives for the 10 to 20 years. So as many of you knew already, that Dune phase 1 is already being constructed, and it envisioned to start taking data in around 2031. With 2 far detectors and 1.2 megawatt beam. And a previous P5 report said that we actually need to build 2 more detectors, FT3 and FT4 for the phase 2, and enhance the beam from 1 to 2 megawatt to 2.4 megawatt so that we can accumulate 600 megawatt kiloton a year. Unfortunately, after Fermilab management put in actually a effort to do a serious study to achieve 2.4 megawatt beam, that ended up requiring replacing the new booster, the current booster, by a brand new booster ring, and that unfortunately would cost extra billions of dollars. And once again, we had to grapple with the situation that we can't afford this much expenditure for the next 10 years. So that's why we had to re-envision the Dune phase 2, but while actually maintaining the same science goal of achieving 600 megawatt kiloton a year. So it so happened that there is a way of getting up to 2.1 megawatt without replacing the booster by making a modification to the current main injector. And right now, main injector cannot accept every bunches out of the booster ring. But by reducing the cycle time of main injector, we will be able to accept all of the bunches coming from booster, and that would actually achieve 2.1 megawatt, close enough to 2.4. And that would cost only a few $100 million instead of billions. And because this modification of main injector can happen much more quickly than building a brand new booster, it turns out that in terms of time scale, we don't need to build a 4th far detector, and we can get by with only 3 far detectors to achieve 600 megawatt kiloton a year in a reasonable time frame. So that is what we meant by re-envisioned phase 2 of Dune that achieves the same science goal as envisioned, but with less cost, so that it can be fit into the budget profile given by the funding agencies. And interestingly, that will leave the 4th cavity at the far side open. So we actually called this is that future opportunities, a module of opportunity. So we actually recommended that DOE would work with the community to solicit new proposals which may actually enhance the science beyond the beam-based neutron oscillation physics, including dark matter searches, the neutron probability decay, and so on and so forth. So that's the way we hope to even enhance the science beyond what had been envisioned by the previous P5. So that's what we meant by the re-envisioned phase 2 of Dune. Now, this list shows what projects we had approved in yes, while what we said no to, and you see quite a few of the projects we had to say no to, and that is shown in solid black. And I already mentioned that onshore Higgs factory is something we had to say no to simply because that didn't fit into the budget. And one thing I have to emphasize is that even though offshore Higgs factory is not onshore and it's an international project, our level of commitment is much stronger than the P5 actually mentioned, the previous P5 mentioned about the Higgs factory back then. That was meant to be IOC, FCCE was still not on the horizon, where they said yes, only for the unlimited budget scenario, but we then said R&D only for low and medium. On the other hand, our recommendation is yes for baseline and a more favorable scenario. Even for the less favorable scenario, we said delayed, but it's meant to be actually yes, just that it comes a little bit later beyond the time frame of 10-year planning. So that this is actually a much bigger expression of commitment for the US involvement in Higgs factory. And for the Generation 3 documentary experiments, many of you know that there have been this incredible merger of various efforts based on xenon around the world, from the US, the UK, Japan, and Europe. And right now, LZ and xenon and TON are competing with each other, and they will eventually join forces. The XLZD get up to 60 or 70 tons of xenon. And in a similar fashion, there are 4 different experiments using liquid argon for document detection around the world, and they are now joining forces that they can actually build 200-ton detector in the future. And as I mentioned already, we recommended one of those, and that needs to be completed in a process defined by DOE and NSF later on. And we hope that at least one experiment can be supported in the US program, and hopefully that can be hosted in the US at the SURF, Sanford Underground Research Facility, which actually is hosting the Dune fire detectors at this moment. So we will see how this process will play out. And finally, IceCube is a project where you can actually do the neutrino astrophysics, and they have already produced a significant result on detecting neutrinos coming from the blazars, that is an active galactic nuclei from one of the nearby galaxies. And also they managed to actually map out the distribution of neutrinos from our galactic disk as well. So this has already started to produce a very interesting neutrino astrophysics results. And IceCube Generation 2 is meant to be a project to make the volume 10 times bigger from the current cubic kilometer to 10 cubic kilometer, together with the radio array on the surface to detect even higher energy component of neutrinos. So we actually supported that. And as I hinted already, some of the decisions cannot wait till the next P5 in 10 years, especially for the Higgs factory. And as Christophe mentioned, they wish to get a endorsement for CERN Council in a timescale of 2028. And 10 years from now will be 2034. So it has to be made decided by the what kind of U.S. contribution will there be well before then. So we recommended yet another panel, which is not the full-blown P5, but more limited panel looking only specifically at the U.S. accelerator-based program, excluding particle astrophysics and the neutrino physics. So that's the panel we recommended, and hopefully that can actually turn around and come up with the quick decisions. So after we released the report, the DOE actually took it very, very seriously, and they already started to implement our recommendations. And to be able to actually work effectively on making decisions on Higgs factory contribution in the United States, the DOE and NSF already came up with a formulation of the Higgs factory joint oversight group, as well as the Higgs factory steering committee. So that is already being implemented. Members of the steering committee are already there. And so this is actually being put together to form various working groups and again get our act together towards the future Higgs factory. And concerning the collaboration between the US and CERN, there had been an MOU signed in the White House. Fabiola came to the US, and she's actually the director of the Department of Energy. And so they actually signed this MOU about a joint statement of intent between the US and the European Organization of Nuclear Research, CERN, concerning future planning for large research infrastructure facilities, advanced scientific computing, open science, and it has a specific recommendation about FCCEE. If the European countries decide FCCEE is indeed the next research facility at CERN. And beyond Higgs factory, and we already have this a discussion by Christophe that there is an ambition to put in the proton machine in the same ring as FCCEE to reach energy scale of about 100 TeV. But as you know, this kind of the machine would require a new technology for the superconducting magnets reaching up to 16 Tesla or 20 Tesla. And that's a technology we don't have today, so that would require further R&D. And the goal here is to come up with an order of magnitude better measurement on Higgs self-coupling beyond high Lumi LHC can achieve, getting down to the 5% level. And there had been also an excitement in the US to actually accomplish the same goal with the muon collider on the Fermilab site. And again, we don't have the technology for it because we need to have a very efficient muon production as well as cooling to make that happen. But if this actually becomes feasible, we can achieve the same science goal, reaching up to 10 times higher energy than LHC with the size of the third of the current LHC ring, so that it would fit inside Fermilab site. And in either case, it's clear that we have to continue on and being more serious about R&D on accelerator technology. So that's why we made a strong recommendation on R&D towards the future facilities building superconducting magnets as well as the basic technology of muon collider. And reaching towards the muon collider, we hope that we can also develop science on its way and a continuous improvement of the Fermilab accelerator complex. And that is the path we called muon shot, in analogy to the moonshot for the Apollo program. And of course, we should also invest in possible wakefield technology on the side as well. And that is the spirit behind the recommendation that we need to invest in the future. And the first one on this list is a vigorous R&D towards cost-effective 10 TeV parton center mass energy collider, which may be 100 TeV PP collider or 10 TeV muon collider. In addition to this technology development, we recommend the specific targeted areas where the research need to be strengthened. 4 areas are theory, general accelerated R&D, instrumentation, and computing. And finally, we recommended the Fermilab needs to come up with a comprehensive plan how this muon shot would pave its way to the continuously producing the world-class science on its way, even if the muon collider may not materialize at the end of the day, because accelerator complex needs to be continuously improved so that we can continuously produce science on its way. So that was the recommendation here. And we also need to have a balanced portfolio from small to large. That's why we specifically recommended a new portfolio supporting small projects on sort of $10 million scale. We call that advancing science and technology through agile experiments. And the abbreviation of that is ASTE, which is a Latin word, which is apparently means javelin. So you need to have a very quick and very fast implementation of projects with clear targets. And that's the meaning behind this ASTE acronym. And DOE really loved this idea. And again, they're trying to implement this. And we also recommended several other small scale, medium scale experiments as well. So this is the response from DOE so far. DOE will not support scope towards the OSCB upgrade 2, even though NSF is likely to support that, so US will be involved in it. The US supports site-independent R&D for G3 dark matter experiment, so they are right now agnostic whether that gets hosted in US or elsewhere, but at least they they want to actually implement one of the G3 dark matter experiments. And for FCCEE, DOE will continue to support and expand participation in the feasibility studies, including expanding efforts to work on the 800 megahertz superconducting RF accelerator cavities and other technical topics and studies as they arise. And concerning IOC, that's yet another option for Higgs factory. DOE and labs will be observers and not officially join the IOC technology network that is funded by Japanese government at this moment, but work on the existing US-Japan cooperation program. And DOE will continue to meet its ongoing commitments with Bell 2, and especially contributions to a Super KKB and accelerator side will be considered in the context of accelerating R&D toward E+E minus luminosity improvements, especially given the fact that this is the first nanobeam collider experiments, which will translate well to the future of FCCEE. And DOE will also implement and execute plan to address this ASTE small-scale program portfolio recommendations. And one difficulty we had is the CMBS4 that was proposed to have two sites, one in Chile and one in South Pole, to maximize science. And it turned out that NSF right now cannot embark the implementation of new projects South Pole because the infrastructure deteriorating, and we are also going to lose access with the cargo plane that is actually going to expire in the next 10 years. But so we have been working very actively on lobbying to replace this cargo fleet that is actually owned by U.S. Air Force to Congress. And so far, the campaign has been quite successful. We managed to get attention from Congress, even though the budget is not appropriated yet. So DOE is now working with the CMBS4 folks to come up with a possibility of doing Chile alone option. But also on the side, we are actively working with the Congress to see if the South Pole can be revived to support the CMBS4. So in the middle of this process, at the end of the snowmass, Dan Garisto, who is the son of the Robert Garisto, who is the executive editor of Particle Physical Review Letters. He's a freelance science writer, and he wrote this article for the Scientific American. The headline says, physicists struggle to unite around future plans. So he was very critical that at the end of snowmass, we are all over the place and we didn't seem to have any consensus on where we are going. But after seeing the P5 report, he actually even did some interviews with many leaders of the community, and he saw that the new roadmap for US particle physics actually did win broad approval by the community, and he became much more positive about it. And better yet, he actually tweeted. So in this tweet, he said, when snowmass ended last year, I wondered how particle physicists were ever going to reach consensus that worked within a budget, was still ambitious, and didn't alienate huge swath of the community. Somehow, the P5 report does all this. So this tweet made me very happy that at least looks like we have accomplished something. So instead of being the most hated man in the community, I think I ended up with a much better situation, which looks something like this. So anyway, a wonderful process, and we are very excited about the program we came up with. Thank you for your attention.
Thank you very much, Hitoshi, and congratulations on this great work of the P5. So
thank you.
Let's open the floor for questions. Yes, Alma.
Hi, I'm Alma from Mexico. Can you comment on the role of the experiments like DESY and Rubin Observatory on dark matter and dark energy researches?
Yeah, so the one sort of sticking point in the U.S. program and Galaxy survey has been that it had been recommended only in the context of studying dark energy so far. So even though there's a wealth of data from Galaxy survey, DOE didn't support analyzing the data, which is already in the can, for the purpose of studying astrophysical probes of dark matter. So we did recommend in this report that the DOE should support that activity as well, given that data is already there once the Rubin, of course, comes online. DESY data already exists, so that we can also study astrophysical probes for dark matter using the same data set. And that is not implemented yet, but at least that was part of a recommendation.
But by the way, the first recommendation was to support Rubin. Hitoshi didn't show that, but I remember.
Because that was meant to be an ongoing project. Yes.
The ongoing project. So Rubin is an ongoing project that had one of the highest recommendations from the
yes
on the P5.
Yeah. I see DESY, the Rubin, and various other projects that are ongoing are already highest priority. And I skipped them because of the time constraint. Sorry about that.
Yes. So one question I have, I probably know the answer, is the gravitational wave experiments. So Cosmic Explorer is not there because it's NSF only? Is that the reason?
That's part of the reason. And also, we had to struggle with this question. To what extent gravitational wave physics is particle physics, in the way we defined it. And the Cosmic Explorer people really wanted to get support from DOE National Laboratories, especially for the vacuum system, because they would require long vacuum pipe, which is quite common with the technology we need for accelerator. But once we looked more seriously at it, we saw the overlap between the interest of the 100 Hertz scale, the gravitational wave, and what we consider particle physics was not great. And also the way we can support NSF projects using DOE resources was quite complicated, and we didn't see a framework for that. So at the end of the day, we had to make a recommendation that we don't embark in this direction for now, but we encourage theories to look into the synergy in science between particle physics and gravitational wave technology for the future.
Thank you. Any further questions for Hitoshi? Online people? Okay, so let's thank Hitoshi again for this very nice talk.
Thank you.
So now we go for a coffee break. So we have a shorter coffee break and we come back at 11, okay?